Okay, welcome. Today we're going to learn about numerical integration. So, as usual, we'll start by defining what we mean by numerical integration and then derive the formula for carrying out numerical integration, and then finally do some examples on numerical integration. So, let's give the definition. So, this is the process of evaluating a definite integral from a set of tabulated values of the function. So, it's in the process So that's what we mean by numerical integration. And then you say, so the general problem might be stated as so this is the problem that we need to evaluate the value of this definite integral. So let's call this one equation 1. So we are given some values of x and y, and then we are interested to calculate the value of this integral, to approximate the value of the integral of this form. So as in the case of the numerical differentiation, so that's what we have. So let's start by the Newton's forward difference formula. So we say let the interval be divided into n equals subintervals such that a is less than a equals to a x naught, which is less than x1, which is less than x2, which is less than x3, which is less than xn, and then xn to be b, with xn given by x naught plus nh, the same thing as just saying xp is the same as x naught plus ph, and h is b minus a divided by n. And then we say, hence the integral 1 becomes call this one equation 2. Simply because we're saying that a equals to x naught and b equals to xn. So then where there's a replaced by x naught, where there's b replaced by xn. So that's why how we are writing the integral 1. So using Newton's forward difference formula, we write I will be the integral from x naught up to xn. So the function can be approximated by this formula here. We have seen it before, how we derive the Newton's formula, Newton's forward formula. Where x is given by x naught plus ph. So this means that dx is the same as h dp. Remember, f of x is what is in the square bracket, just from definition. So therefore now we can write, so therefore replacing dx by h dp, we have the integral as h integral from x naught to xn of f naught plus p plus p minus 1 So I have changed the integral from being with respect to x to being with respect to p from this relation here. And then you say, therefore, on simplifying, we have I, which is the same as the integral from x naught to xn of f of x dx is given by nh f naught plus n over 2 plus n into 2n minus 3 plus n into n minus 2 square over 24 I'll call this one equation question 3. So remember, at this point here, we are getting this integral by simply saying x naught is the same as n, then this is the same as n. So that's why we have n points from 0 to n. So that's why we have this relationship here. So let's then you say from the general formula. So this is a general formula. 3 is a general formula. For carrying out that integration. So we say from this general formula, we can find different integration formula by putting n equals to 1, 2, 3, 4, etc. So this formula is also known as the Newton's code Cotes clause formula. So then we want to use the Newton's closed quadrature formula to derive the expressions of the formula, expressions for Simpson's third rule formula, Simpson 3th rule formula, and then trapezoidal formula or rule. So let's start by trapezoidal rule. I know trapezoidal rule is not new to us. We have interacted with this formula from our high school. So then we say putting n equals to 1 in formula 3 and taking the curve y equals to f of x through the point as a straight line, i.e. polynomial of degree 1, so that the difference higher than 1 becomes 0, we get I1 will be integral from x0 to x1 of f of x dx equals to, so n is 1, so n times h is just h, f0 plus a half which is the same as h into f0 plus a half into, you remember definition of the forward operator? So this will give us h over 2 into f0 plus f1. Similarly, I2 will be the integral from x1 to x2 of f of x dx, which will be given by h over 2 f1 plus f2. I3 will be given by integral from x2 to x3 and then the next etc up to the point we have in equals to the integral from xn minus 1 to xn of f of x dx, which will be given by h over 2 into f n minus 1 plus fn. Adding all this, expressions and using interval additive, we obtain this. Is what you mean that now I will be given by I1 plus I2 plus I3 plus up to plus IN. So which means that then we'll have I equals to the integral from x0 xn of f of x dx will be given by h over 2 into f0 plus 2 f1 f2 f3 up to fn minus 1 plus fn, i.e. I, which is given by the integral from a to b of f of x dx is h over 2 into f naught plus fn plus twice f1, f2, f3 up to fn minus 1. So this is what is called the trapezoidal rule. So this is the trapezoidal rule. So remember, h is given by b minus a over n. And then number 2 is what we call the Simpson's third rule. So Simpson's third rule, we put 2 for n. So say putting as a parabola, i.e. polynomial of degree 2, so that the differences of order higher than 2 vanish, that is, they approach 0. We get I1 integral from x naught x2 f of x dx equals to 2h into f naught plus 1 over 6 so this will give us h over 3 when you simplify into f naught plus, or let's just simplify together here for you to see what is happening. So we have 2h into f naught plus, definition of this one is given by f1 minus f naught plus 1 over 6 into f2 minus 2f1 plus f naught. You remember how we used to simplify this one when you are introducing our differences? So when you put together, so it's like we have 2h into, let me put 2 inside, so okay, just 2h, and then f naught minus s, so this one and this one cancels, so it's like we have 1 over 6, so this would be plus 2 over 3 f1 minus a third minus a sixth f naught plus a sixth f naught. This is the same thing as saying I can write this one as 2h into 1 over 6 f2 plus 4 f1 over 6, so that this is the same thing as just 2 over 3 plus 1 over 6 f naught, just to ensure that I have the common denominator 6, and then I factor it out, so I have that 2h over 6 into f2 plus 2 plus 4, not 2, 4 f1 4 f1 plus f naught. So the same as h over 3 into f2 plus 4 f1 plus f naught. So this is I1. Similarly, I2 will be given by integral from x2 to x4 of f of x dx, which will be given by h over 3 into f2 plus 4 f3, then plus f4. Remember, this I1 can just be written as h over 3 into f naught plus 4 f1 plus f2. And then I3 will be the integral from x4 to x6 of f of x dx, which is h over 3 into f4 plus 4 f5 plus f6. We can as well define I4, which will be the integral now from x6, x8, f of x dx, six plus 4 f7 plus f8. In a similar manner, we can go ahead and then define the last integral in to be the integral from x h over 2 into fn minus 2 plus 4 fn minus 1 then plus fn. So therefore now doing the same thing you have done in the first case. So remember this is the limits will be now, this is the multiples of 2, so will be x to n minus 2 actually, so then let me just now write it. So then okay, 2n, so we have 2n 2n 2n. So i.e. in general, i.e. I, so not really i.e. So then therefore the total integral is I1 plus I2 plus I3 plus I4 up to plus In, which is I equals to the integral from x0 to xn of f of x dx equals to h over 3 into f0 plus 4 into f1 plus f3 plus f5 plus 2n minus 1 plus 2 f2 plus f4 plus f6 plus f8 plus f2n minus 1 minus 2, then plus f2n, i.e. the integral I from a to b f of x dx is given by h over 3 into f naught plus f2n plus 4 into f1 plus f3 plus f5 plus f7 f2n minus 1 plus 2 into f2 plus f4 plus f6 plus f8 plus f2n minus 2 or just say I equals to the integral from a to b of f of x equals to h over 3 into x plus 4 o plus 2e, where x means sum of endpoints, end ordinates, and then o means sum of odd ordinates, and then E means sum of even ordinates. So this formula here, is what is called the Simpson's third rule. This is the Simpson's third rule. So for you to apply this rule, you need to remember this. So let's call it star. Let's call this rule star. This rule requires to apply star, it is required that the whole range i.e. the given interval must be, or respect this word must be divided into even number of equal subintervals. Since we find the area of two strips at a time. So please don't forget this. So the last formula, an exercise discuss error estimate in both trapezoidal rule and Simpson's third rule. You might find it in exam. So take it seriously. You'll find a question on this one in the exam. So the last is Simpson's three-eighth rule. So for Simpson 3/8 rule, we take 3 points, or we take 3n, we take n as 3. So we say setting n equals to 3 in equation 3, so we're taking for xi 0, 1, 2, and 3 as a polynomial of degree 3 so that the differences higher than the third order vanish. That means they approach 0. We get so the first integral I1 will be from x0 to x3 of f of x dx will be given by 3h into f0 plus 3/2. Remember, all these things we are getting them from the formula of 3. One over 8. So you are replacing n for 3 in formula 3. That's how we are getting this. So when you do simplification, you get 3/8 into over 8h into f0 plus 3, f1 plus 3, f2 plus f3. So similarly, I2 will be given by the integral from x3 to x6. And when you do the simplification, you get 3/8h into f3 plus 3f4 plus 3f5 plus f6, and then I3 will be x6 to x9, so we should be 3/8h into f6 plus 3f7 plus 3f5 f8 plus f9. We can also define I4 as the integral from x9 to x12 fx dx, which is 3 over 8 h into f9 plus 3 f10 plus 3 f11 plus f12 etc. Then we have, in general, we have this. In general, I n is given by integral from x 3n minus 3 up to x 3n of f of x dx, which should be given by 3 over 8 h into f 3n minus 3 plus 3n minus 2 plus 3n minus 1 plus 3n. So therefore, in the usual way, the integral I will be the I1 plus I2 plus I3 plus IN, which will be given by integral from x naught to x3n of f of x dx equals to 3 over 8 into f naught plus 3 into f1 plus f2 plus f4 plus f5 plus f7 plus f8 up to plus f3n minus 2 plus 3n minus 1 plus 2 into f3 plus f6 plus f9 plus f12 plus f3n minus 3 and then plus f3n. That is that the integral from a to b of f of x dx will be 3 over 8 h into f naught plus f3n plus 3 into f1 plus f2 plus f4 plus f5 plus f7 plus f8 plus f3n minus 2 plus f3n minus 1 plus into f3 plus, there's a 2 here, f6 plus f9 plus f12 plus f3n. So f 3n minus 3 So this is what we call the Simpson's 3/8 rule. So this is Simpson's 3/8 rule. Note, to apply Simpson's three-eighth rule, the number of the subintervals must be a multiple of 3 and then as an exercise, discuss the error estimate in the Simpson's 3/8 rule. You will find this one also in exam. So we'll stop there for today, and then the next lesson will be doing examples on numerical integration. Thank you.